The second kind of product that we're going to consider is the dot product of vectors, and it'll be explicitly written as a dot, and importantly, it'll be the combination of two vectors as the input. So this differentiates it from the scalar, which would be 2 times a vector or 5 times a vector. Here we have one vector times another one. The output is also a little different. Instead of being, as you might expect, when we combine two vectors, we actually don't get a vector back, we just get a scalar back. Now, how is this dot product defined? This might seem a little unobvious or unintuitive at this point, but we'll see how it plays out. If we have v dotted with w, that's how we'd say this, v dot w, we can compute that explicitly as v, its length, that's important here, length of v, times the length of w, and the most interesting thing, this is really a new component here, the cos of the angle between v and w. Okay, now this is going to take a little bit of practice. You haven't seen it before. Many of you will have seen it, but this involves then how these two vectors are positioned relative to one another, and do they point in a comparatively similar direction or a vastly different one. Now let's take a look at our basic identity vectors here, or our unit vectors, sorry, unit vectors. And these unit vector I and I are the vectors in the x direction, or the x-axis. So if we take our two vectors I, and let's take another one just for fun, I, same length, then by this definition, I dotted with I is going to equal, test yourself if you've seen it before for a second, then we'll do the calculation. Well, it's going to be the length of I times the length of I times cos of the angle between them. Well, vectors like this that are parallel and pointing in exactly the same direction have zero angle between them. They're pointing exactly the same direction, so our angle would be 0. And because I is a unit vector, the whole point of being a unit vector is that the length of it is exactly 1. So we get 1 times 1, and cos of 0, also better known as 1, and we get, whoops, we do not get 0. We get 1 at the end of all that calculation. So in some sense, as we'll see, this tells us that I and I are compatible with each other, that they point in a common direction in some sense. This 1 being positive is going to tell us something about how similar the directions are. We're going to see that in contrast with the next example when we look at the unit vector in the x direction, but then add the unit vector in the y direction, or along the y-axis. And so this one here is, again, the unit vector in the x direction. Or along the positive x-axis. So take a look at this. Ask yourself which of these values here we would get if we use these two special unit vectors, and we'll take a look at that in 1 second. Okay. One of the vectors is I, pointing in the positive, so let's get some axes here. The x and the y axes are here. And then if we have our second vector, which would be j here, then I dotted with j is going to equal the length of the I vector and the length of the j vector multiplied times the cos of the angle between them. And this time, though, they're following the axes, x-axis and y-axis, and so the angle there is going to be 90 degrees, or in radians, pi over 2. And what we get out of that is the same unit length, so the lengths are 1, but cos of pi over 2 is 0. So overall, we get a 0 value for this dot product. So we see a dramatic difference between I and j's dot product, which is 0, and I dotted with I, which was 1, too many dots. I dotted with I is going to equal 1. And if you've done any physics, this dot product gets into the idea of projecting vectors onto other vectors, so force components, things like that. It also shows up in finance when you look at directions or decomposing data sets. So this idea of a dot product as being one vector sort of being squished down into the direction of the other is a very, very important one beyond the scope of this course. We'll use it a lot, but there's a lot more to it as well. There's some important features that we can get out of this idea, though. If V and W are perpendicular, then what can we say about the dot product? Well, if that's the case, if they're perpendicular, then the angle between them is going to be pi over 2, 90 degrees. That's what perpendicular means. And as soon as we say that, then their dot product will be the length of V times the length of W times the cos of the angle between them. So if they are perpendicular, so we have an angle of pi over 2, this is always going to be a 0 term. So we're always going to get a 0 value. So if we have two vectors that are perpendicular, their dot product will be 0. Now, just to turn that around, if we can see two vectors and we take their dot product and we get 0, does that mean that they're perpendicular? Well, let's take a look. V dotted with W is the length of V times the length of W times cos theta, the angle between them. And so it seems pretty clear, actually, that therefore, yes, theta, cos of theta must equal 0. And the way that's going to work is that the angle is going to equal pi over 2. And again, if we're measuring angles with respect to each other, we take the smallest one. It'll never be any other higher number than pi over 2. And, well, this is fantastic. Oh, wait, but that's not the only possibility. If we take a look at this expression here, is there any other choice? Yes, there certainly is. So it's possible, if you see a dot product that equals 0, and sorry, let's put that at the end here. If this equals 0, then the cos term could equal 0, or either one of those other lengths could equal 0. Length of V could equal 0, or length of W could equal 0. In other words, one of the vectors is the 0 vector. That is another way that we can get a dot product value of 0. So this is important. We're going to use this all the time as we study gradients and directional derivatives. If we have two non-zero vectors and we get a dot product of 0, then guaranteed the vectors are perpendicular. If we just pick two random vectors and we find their dot product is 0, it's most likely, in most interesting cases, that the angle between them is 90 degrees or that they're perpendicular. But we do have to check for the exceptional cases where the vectors themselves might be 0 in the first place. They might be the 0 length, no direction vectors, and that would be a slightly different scenario.